Hi all, welcome to our final part. Today we are focusing on testing and monitoring, which are crucial aspects that make the difference between a prototype and the production system. Before we dive into implementation, let's understand why testing an AI system is fundamentally different from traditional software testing. In AI systems, we have what's called the testing pyramid. At the base of it, we have the model testing. We test the model's core functionality. Think of this like testing a car's engine. We need to verify the basic input-output functionality, the memory management, and the response generation. Our test access code handles this level of testing. Next is the integration testing. The middle layer tests how components work together, like checking how a car's engine works with the transmission. This includes adapter switching, language detection accuracy, and end-to-end query processing. This is what our test endpoint code covers. And the third is performance testing. The top layer verifies production readiness, like testing a car on different road conditions. We check the response latency, the memory usage, and the error handling. This is handled by the test inference code. Now, talking about monitoring, AI systems need three types of monitoring. First is the technical monitoring. Just like how a car's dashboard shows speed and fuel, we track the system's GPU utilization, memory usage, and request latency. Second is the functional monitoring. This is like checking if your car is staying in its lane. In our project perspective, this is like checking the response quality, the language detection accuracy, and the error rates. Third is the business monitoring. It's like tracking your journey progress. In our context, this is tracking query volumes, user satisfaction, and cost per query. Now that we know the different types of testing and monitoring strategies, let's implement our testing suite first. First, we are looking into the test access file. This ensures our setup is correct before we attempt deployment. Think of it like your pre-flight checklist. The file performs two critical checks. First, it verifies that we can access the Hugging Face model we'll be using, ensuring that our token is valid. Second, it confirms that we have the necessary permissions to use AWS SageMaker services. In test Hugging Face access method, we verify our Hugging Face setup is attempting to get information about a chosen model. The test SageMaker access function checks our AWS permissions by trying to list SageMaker endpoints. If either test fails, we'll know exactly what needs to be fixed before proceeding with deployment. This prevents us from discovering permission issues or access problems in the middle of our deployment process. Now let's look at our test endpoint code. This verifies our deployed model is working correctly. After deployment, we need to make sure our endpoint can actually process customer queries and return meaningful responses. This file sends a simple text message like "Hello, how are you?" to our deployed model and checks if it responds appropriately. The test includes important parameters we would use in production, like maximum new tokens, which limits the length of the model's response, and temperature, which controls how creative or focused the response should be. The script converts our text message into JSON format, sends it to our SageMaker endpoint, and then decodes the response. Any errors during this test would indicate issues with our deployment that need to be addressed before going live. Next, we are testing our inference. Inference testing uses sample queries in different languages. Each query represents a real customer support scenario. The test verifies language detection, adapter loading, and response generation. For each query, our test logs the incoming message, processes it through our customer support inference handler, and logs the response to verify that the correct language is detected, the proper domain is identified, and whether appropriate response generation is performed. Okay, now let's look into how we are implementing monitoring for our multilingual support system. Monitoring is absolutely crucial. Without it, we would be flying blind once our system is in production. Let me show you how we are going to track every aspect of our system's performance. Let's start with our monitoring dashboard class. The first thing we do is initialize a CloudWatch event. CloudWatch is Amazon's monitoring service. Think of it as your system's health tracker. Just like a fitness tracker monitors your heart rate and steps, CloudWatch will monitor things like response times and memory usage. We will monitor our GPU memory, which is our NVIDIA A10 GPU running on our G5 instances. So here's what we are doing. We are using a tool called NVIDIA SMI. This is like having a direct line to your GPU to ask, hey, how hard are you working right now? This returns three crucial pieces of information. One is memory used, second is total memory, and the third is GPU utilization. You want to know how much you are using out of the total available memory. Okay, so once we have these numbers, we send them to CloudWatch.
using the put metric data function. But here's the interesting part. We are not just sending raw numbers. We are organizing them into what CloudWatch calls a metric data array. Each metric has a name, a value, and most importantly, a timestamp. This timestamp is very important because it lets us track changes over time. Okay, now let's talk about our dashboard creation. A CloudWatch dashboard is like your system's control panel. We are creating two main panels, or we can call it as widgets, as CloudWatch calls them. The first widget tracks inference latency, like how long it takes our system to process a request. The second tracks the query length. Why these two? Well, they often have a relationship. Longer queries might take more time to process, and we want to understand that relationship. Each widget is configured with a period of 300 seconds. That is 5 minutes. This means CloudWatch will aggregate our data into 5-minute chunks. So why 5 minutes? Because it's a sweet spot which is short enough to catch issues quickly, but long enough to avoid overwhelming our system with constant updates. Okay, finally, let's look at our view metrics method. This is where we can actually see what's happening in our system. We are pulling data from the last hour, but there's something clever happening here. Instead of just getting raw numbers, we are asking CloudWatch for both average and maximum values. This is incredibly useful because it helps us spot not just ongoing issues, but also brief spikes that might indicate problems. One last thing that's really important. Notice how we've implemented error handling throughout the code. When you're monitoring a system, your monitoring itself needs to be robust. It's like having a backup camera for your backup camera. You need to know if your monitoring system itself has issues. Okay, now that we looked into the monitoring code, let me show you how the CloudWatch dashboard actually looks like in practice. Okay, now let's look at our first graph, the average inference latency. This is measuring how long our model takes to respond to queries, which is measured in seconds. The y-axis goes from 9 seconds to 16.5 seconds. And we are looking at a time window from 7 p.m. to 8 p.m. UTC. Notice that interesting spike around 1915. Our latency jumped up to about 16.5 seconds before gradually decreasing. This kind of spike could indicate heavy load on our system, or perhaps a particularly complex query that took longer to process. For the second widget, we have average query length. This graph shows us how long our incoming queries are, basically how much text our users are sending us. The y-axis shows us the count ranging from 39 to 72 characters. There's an interesting correlation here. See how the query length also peaked around 1915? This suggests that longer queries generally take more time to process, which makes intuitive sense. Our system had to work harder with more input text. At the top of the dashboard, we have some really useful controls. You can select different time ranges using the calendar icon, choose your time zone. We are currently in UTC. Refresh the data using this circular arrow, and we can add new widgets using this plus button. The Actions drop-down gives you even more options like sharing the dashboard or downloading the metrics data. These visualizations are invaluable for both debugging and optimization. If we notice consistently high latency, we might need to optimize our model or upgrade our infrastructure. Or if we see query lengths trending upward over time, we need to adjust our system to better handle longer inputs. One really powerful feature is the ability to hover over any point on these graphs to see exact values. You can also zoom in on specific time ranges by clicking and dragging across the graph. Let's analyze the output from our test inference script. We test runs multiple queries across different languages and domains to verify our system's capabilities. For the first test query, our system has correctly identified it as Spanish and the domain as technical. This is about a technical query of login issues in Spanish. We see that the response has taken around 18 seconds for a query length of around 75 characters. The system has generated a detailed response in Spanish about account access issues. Notice something interesting in the metrics. Our response times are consistently around 17 to 18 seconds for most queries. This shows our system has stable performance regardless of the query length. Next, we test the inference file across different languages and domains. The second query is similar to the first one. It is Spanish and technical. For Spanish technical queries, we test through different issues like login, app crashing, or Wi-Fi connection. We see how the system responds for different types of technical errors. Next, we send a query in French asking about a billing question. We test the system on different billing queries like extra charges questions, subscription cancellation, and we see that the response time still remains consistent across different types of errors. And at last, we test the system for Russian technical queries. We test them upon software update questions, autosave functionality issues, new version inquiries. But do you see an interesting pattern in the performance improvement for Russian queries. Other queries usually take around 17 to 18 seconds, but for some Russian queries, we see the output in 7 to 8 seconds. This might indicate better caching or adapter optimization for certain queries. But overall, the system shows strong domain classification. The technical queries are correctly identified across all languages, billing queries are properly routed, and the responses stay relevant to the domain. But do you see one minor issue? This is a French query about monthly costs. It was incorrectly identified as a Spanish query initially, but it still provided an appropriate response. This suggests that our language detection system could still be improved for certain cases. We need to train our adapter more relevantly to address these queries rather than just keyword matching. But overall, the test suite shows that our system is successfully handling multiple languages and maintaining consistent response times.
Before we wind up, let's quickly review what we've built through this series. First, we've implemented a multilingual support system with LoRa adapters. Along the way, we saw how to set up efficient pipeline, comprehensive testing, and production monitoring. Now that concludes our series. You now have a production-ready multilingual support system with proper testing and monitoring. If you've built something with this system, share your experiences in the comments. Don't forget to like and subscribe for more AI-related content. Thank you.